So Valeria Tomaselli is a senior engineer and project leader at STMicroelectronics, Catania, Italy. She holds a master's degree in computer engineering from the University of Catania. Since 2003, she has been working at STMicroelectronics in the System Research and Application Group, where she conducted research activity and developed application solution in the field of image processing and computer vision. Her current project focuses on machine learning, deep learning, artificial intelligence applications and tools, as well as on brain-computer interface research. She is author of patents and papers on image processing, computer vision, and artificial intelligence. She has also participated in numerous national and international research projects. Thanks, Valeria, for your time and your patience, especially because we are running out of time. You have your 25 minutes plus 5 minutes Q&A slot. Please, the floor is yours. Thank you.
Okay, thank you, Danilo. Thank you, all the organizers, and hello, everybody. I will give you a brief introduction on the on-device learning research activities that are carried on at STMicroelectronics, and then I will focus on the main topic of my speech, that will be on-device learning with the EcoState network, considering then some future challenges for on-device learning. First of all, I would like to start with a very brief introduction. We all know that at the beginning of artificial intelligence, the main paradigm was centralized AI. This means that both training and inference happened only on the cloud, where we can consider that we have almost unlimited resources in terms of memory, of time, because we can launch our training in background mode and so on. Today we are in a hybrid phase. We are in a partially distributed AI, where the training still happens mainly on the cloud, and the models can be deployed to the edge devices, so also on microprocessors, microcontrollers, and the inference happens on the device. In future, we foresee that there will be a different scenario, fully distributed AI, where the AI models can be modified and trained at the edge directly on the microprocessors, microcontrollers, using local data. Nowadays, there are many different tools that allow to deploy a trained model into an edge device. I'm listing here only some of them, but these frameworks allow to optimize the model, to compress it, to quantize it in order to fit with the device constraint. But all these frameworks don't provide the training functionalities. Obviously, as I already said, the training on the cloud has many advantages, because you can use a very huge data set, thus producing very general models. But on the other side, we have some problems. We have privacy concerns, because we need to send our data to the cloud, and moreover, there are also bandwidth problems, and models cannot be personalized, tailored on the final user. So the training on device can cope with some of these drawbacks, allowing us to enhance the privacy, to have offline learning, to have personalized models, and to have also federated learning. Here, a list of some research activities we are carrying on at STMicroelectronics, starting from the more traditional ones. For example, we are trying to understand how to efficiently implement backpropagation on STM32 microcontrollers, because obviously backpropagation is a process that is data hungry, time hungry, it is unpredictable in time, so there are many problems to be addressed. But But we are also working on personalization. So we are studying how to train and adapt pre-trained models on local data acquired by ST sensors. We are also investigating the federated learning paradigm in STM32 open development environment. And last but not least, we are exploiting also some new paradigms. And in particular, in this talk, I will present training from scratch in the tiny edge device using the EcoState network. This activity was carried on together with the University of Messina in Sicily. Let's start with the objective of this activity, the case study. We want to address change detection in time series data. So when we have time series data, change detection refers to the recognition of a persistent change in the time series. So it is a concept that is a bit different from the anomaly detection, because we don't want to identify a glitch, a spike in this time series, but a change. So a deviation from the normal distribution, from the standard distribution over the time. And this change can be due to different motivations. It can be due to an unforeseen evolution of the process generating the data, or a fault in the machinery. So it is important to identify a change variation sadly in order to act. We defined some requirements for our on-device learning method. We want a limited memory because we want to run it on a microcontroller, and we want also limited memory to buffer data that are used for training, for on-device learning. We want a fixed on-device learning time. Data cannot be stored for undefined time, and we want to avoid the backpropagation. We want a very limited user interaction. And we want to have the freedom to implement the on-device learning with the desired method. We want the on-device learning time being much less than the data acquisition time, and hopefully to be less than 1 second. So let's see if we are able to achieve them. First of all, we want to provide a brief introduction on reservoir computing and the EcoState network. Reservoir computing is a framework which derives from recurrent neural networks, and it has two main concepts. It has a the dynamical part, which is a reservoir that in this feature on the right is depicted within the gray area, and there is a readout, a not recurrent part, which are the weights between the reservoir and the output. The EcoState network are the main framework for reservoir computing, and they have the peculiarity that they have fixed reservoir weights. This means that when we want to train this EcoState network, we need just to update the readout. So just the connections between the reservoir layer and the output layer. This means that we can increase the training time. We can have faster training time. Obviously, if we don't set properly these reservoir weights, we can end with a poor accuracy of our model. So it has been seen from different state-of-the-art approaches and papers that two properties need to be achieved when initializing these reservoir weights. They are the sparsity and the EcoState property. So usually we use a huge reservoir that are recurrent connections, but many of them are sparse. These allow to have different independent subnetworks that produce different reservoir states to the same input. So this property increases the nonlinearity of the system, the capability of the system to extract non-linear temporal features. And the second property, the echo state property, refers to the gradual memory fading, which is the property according to which the history, the input history influence on the reservoir states needs to decrease over time. And this property is guaranteed if the spectral radius of the reservoir weights matrix is less than 1. The spectral radius is the maximum eigenvalue in a module. So if we meet these two conditions after an experimental phase, we can just learn our readout. Here in this picture in solid black, I'm representing the fixed connections and the mandatory connections. In the dashed lines represent the trainable, the only trainable connections. In red, we have the optional connections. How to address the change detection with the echo-state network. We can train echo-state network as an autoencoder. The autoencoder, I recall, but it has been said during today's seminar that is a way, a network that try to reconstruct the input. So the number of neurons at the number of output neurons equals the number of input neurons, and the reservoir in this case acts as the latent space, the code. The code of this autoencoder. And for training an autoencoder, we want to minimize the distance between the output and the input. So we want to minimize the reconstruction error. So for this reason, looking at this equation, considering that Y is the output matrix, it is in echo-state network, it is computed through X times theta, where X is the state of the reservoir and theta is the readout, our matrix, our unknown. We want to minimize the reconstruction error, so we can write down this mean square error, this cost function that can be minimized through the multivariate ridge regression. In this case, we have a normal equation where we have also the lambda parameter, which is the ridge parameter. And this parameter it acts as a regularizer that avoids overfitting and reduce the variance. This is our on-device learning phase. So we are completely avoiding backpropagation. Once we obtain this readout matrix, then obviously for identifying a change in our time series, we need to identify a threshold. So we compute our output, measure the distance with respect to the input, and then we need to compare it with a threshold. So setting this threshold properly is of paramount importance. And we calculated this threshold connecting it to the median of the train mean square error. At inference time, when we give an input to this echo-state network, we update the state, and then we also update the output. We measure the reconstruction error and compare it with this threshold. If this threshold, the reconstruction error is greater than the threshold, we are identifying a change. Otherwise, the behavior is normal. But what is the challenge now? To deploy this methodology on the microcontroller can be challenging because, as already said, current frameworks don't allow to have on-device training. So we tried to overcome this problem through this methodology. First of all, we created a novel custom ecostate network layer in Keras. Then we exploited the functionality provided by the STM32Cube.ai tool, which is the support to complex Keras custom layers. And finally, we wanted to build a test bed to see if this approach can work in reality, and also to measure the performances. So first of all, we started creating a custom ecostate network layer in Keras, inheriting from the TensorFlow Keras layer class. And in particular, in the init method, we initialized all the ecostate network hyperparameters, taking into account the sparsity and the ecostate properties. Then we have overridden the fit method, replacing it with the multivariate ridge regression. We can observe this the created Keras model using some visualization applications such as Netron. Then we tried to import it using STM32Cube.ai because it supports complex Keras custom layers. So in the first phase, we pass the generated Keras model together with a JSON file where we point to the Python implementation of our custom layer. And the STM32Cube.ai will generate the C code for all the layers it already knows. And for the custom layer, it will generate a template file that needs to be filled with the custom C implementation. So once the user fills in the boilerplate, the template C file, we can have the second phase. So we can pass again to STM32Cube.ai the Keras model and the JSON file, but in this case we are referring to both implementations, the Python one and the C one. In this way, the STM32Cube.ai will be able to generate our C code. And finally, we can also validate this C code against the original Keras model. So we can run the validation process by running the Keras runtime that has in input the Keras model and produces one output. And at the same time, we run the compiled C code on STM32 board to have the output. We compare both outputs to see if the conversion has been done properly. And from this screenshot, we can see that the L2 error is very low. Okay, then, as I said, we wanted to experiment, to have a real experimentation of the proposed methodology. And we decided to analyze the vibration signals recorded by a 3-axial accelerometer to assess the working conditions of a DC motor. And we then were able to measure also some metrics. We built a test bed just for demo purposes. So as you can see, it is composed by Lego bricks. So it is just for demo, obviously. And it is composed by a DC motor that can be powered with 5 volts or with 3x3 volts. And the power supply can be chosen according by means of a relay. Then we have a board that is a CloudGem board equipped with an STM32F4 microcontroller unit having this characteristic 500 kilobyte of flash, 96 kilobyte of RAM, and 84 megahertz as maximum frequency. And this board is also equipped with the 3-axial accelerometers that will be useful for identifying the vibrations produced by the motor. We designed an ecostate network for this case. Since we train it as an autoencoder, we will have 3 inputs and also 3 outputs, because 3 is the number of accelerometer signals we are receiving in input. after some experimentation, we found that 35 neurons in the reservoir state are enough for this specific use case. And moreover, after different experimentation, we decided to use just 150 samples to perform our on-device learning. This was achieved. This is a good trade-off between performance, accuracy, and also the time to acquire data. Consider that the accelerometer is running at low power and it runs at 50 Hertz. So we need 3 seconds, about 3 seconds for acquiring 150 samples. Then I said that we need to set the sparsity and the spectral radius of the reservoir weights matrix, and after some experimentations, we found the best values for our use case. And then I will show you now the video demonstrating how the system works. First of all, when the user press the button in the board, the training phase is started, and it goes on until this user green LED is on. When it starts blinking, this means that the training is over. So now it is in the inference mode. The user LED is off, and it is a normal condition. But if we then simulate low power anomaly, then the green LED is on, and this means that the system is identifying a change. Then we go back to the 5 volt, and the LED is again back to off. We are introducing also disturbance in the motor, and also in this case, this is identified as a change in the normal condition. We can also simulate lack of energy, and this is suddenly identified. In fact, the green LED, the user LED, is green. Then we performed another experiment. In particular, we trained the system when the disturbance was on. So we are instructing the system as this condition is normal. So now the system is learning that this is the normal condition. Okay, the training is over. And as soon as remove the disturbance, it is considered that the LED is green, and it is identified as a change. When the disturbance is on, it is recognized as normal. This was a stress test that we wanted to do. Thanks to this test bed, we were able to acquire data and to analyze them from the numerical standpoint. In the first experiment, our goal was to recognize the occurrence of a power loss in the test bed. So we trained the model with the vibrations produced by the motor power supplied at 5 volts, and then we decreased it to 3 by 3, and after 2.5 seconds. The system understands that there is a change starting from 3.5 seconds. So it takes 1 second to identify there has been a change. But this 1 second, this latency is due to the fact that we are introducing also a temporal filter to the output of the networks to avoid to have glitches. And so we are considering a change when it persists over the time. But it can 1 second latency can be considered acceptable in this kind of use cases. A similar experiment was conducted for the opposite case. So we are training as normal. With the vibrations produced by the motor power supplied at 3 by 3, and then we are increasing the power supply to 5 volts. Also, in this case, we can see that the red line starts about 1 second after the change in the system is introduced. And this is the latency of our system. These are this is the numerical analysis we got. We have the confusion matrix and the numbers for precision, recall, and F1 score. So we can see that they are quite high. We have the 15% of false positives, but they are reduced at application level, introducing this temporal filter on the output that I already mentioned. So we have at the end, we have less false positive than this 15%. Important numbers are also execution time and memory footprint. The memory needed for on-device learning is just 45 kilobytes. On-device learning time happens in 358 milliseconds. This means that we can have 2.8 on-device learning per second. The data acquisition time, as already said, is 3 seconds. So we need 3 seconds for acquiring all the data that have to be used for learning. Inference time, so when we don't perform training, but just update the state and then the output, we need just 0.83 milliseconds. And this is the flash memory that is required for storing all the weights that are unchanged. So the reservoir weights, just 5 kilobytes, and the RAM of only 500 bytes. These are the weights for of the readout. So finally, yes, we can see that we have met all the requirements that we set at the beginning of this activity. We have a limited memory. We have a limited memory also to buffer data. We have fixed the on-device learning time. Data stored for about 4 seconds, then they are disregarded. We are avoiding backpropagation because we are using the multivariate ridge regression in place of it. There is a very limited user interaction because the user just press a button to start the on-device learning phase. And there is the freedom for the user for defining his own training procedure because we are exploiting the custom layer provided by STM32Cube.ai. And finally, we have an on-device learning time, which is less than 1 second, and it is much less than the data acquisition time. Which are possible future challenges for on-device learning? Obviously, this is a first step. We are moving first passes in on-device learning. In future, we would like to have scalable on-device learning. As you see, we train from scratch the model, discarding all the previous history. But what about if we want to add more normal states for our system? Can we scale up? Can we add classes? Can we remove them? And moreover, thanks to on-device learning, we want to increase the object's lifetime, having the possibility to identify suddenly if there is a problem in a machinery. And finally, is it possible to have an end-to-end learning, so a system that measure the data, learn from them, and then act to solve the issue when it happens? So these are some of the future challenges, but obviously there are also many, many others. Thank you.
Thanks, Valeria, for your great talk and for all the content that you kindly shared. There is a time limited because we are out of time. Apologize to everyone, my fault in keeping strictly the time. Question number 1, how was the best value of sparsity and other metric was found?
Sorry?
How was the best value of sparsity,
okay,
and other metrics was found?
Okay, the other metric, the eco-state property. Okay, so we collected data from our test bed and then analyzed the different values for both the sparsity and also for the spectral radius. And there were some graphs showing the accuracy reached for each value that we tested. Obviously, we choose the values giving the higher accuracy, the higher performances.
Thank you. Second question, how effective is the model when there are multiple normal conditions? For example, an adjustable fan with speed of 250 RPM, 750 RPM.
It is a very interesting question, but it is in our future challenges, because up to now we are discarding all the previous normal conditions, so we are training from scratch. Our future work will be in this direction for sure, how to scale up with our model, how to add more normal classes. This is very interesting and is challenging for our future research.
Thank you so much, Valeria. That forum was possible thanks to the tinyML Foundation support and all the support from the strategic customer, which are helping a lot in providing resources to make sure that this forum and other events and other interesting events will happen in the future. So just to thanks also and list the executive strategic partners: ARM, Edge Impulse, Qualcomm Research, Sentient, and the Platinum Strategic Partners: DeepLight, Clickattack, Reality AI, Renesas, Sony Semiconductor. The Gold Strategic Partners: Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SensiML, STMicroelectronics, Synaptics, ScienceSense, and all the silver strategic partners. Thanks again to stay with us yesterday and today, and I hope it was a valuable experience. Thanks and see you soon. Bye.